There are no new LAN network elements, other than the stationary sensors, which have negligible cost. The existing roads on which the LAN vehicles would initially run could be replaced, as desired, with the equivalent of walking and cycling paths. NetSair for the US would require fewer than 10 airports, built in relatively remote rural areas with very small terminal equivalents. The cost for building these would be more than recovered from the value of the land of the redundant CUTS commercial airports that exist in all larger cities. WAN guideways are almost all viaducts or bridges. They are cable-stayed structures with 3 to 9 light beam-based track spans. The spans are stiffened laterally with a combination of light shear walls and rods. Guy wires are connected as needed to deal with lateral dynamic loads from wind or vehicles. In the base configuration, there are support towers or columns, typically every 50 meters. These are strong enough to support the static load of the guideway and the dynamic load of moving vehicles. The bending moments from vehicles and the wind effects are largely handled by the guy wires. The current choice of beams, tracks, cables, lateral stiffeners, and covers have a mass under 10 kilograms per meter. 50-meter spans then put a static compressive load on the support towers, less than 5 kilonewtons per track. On all but the intercity guideways, the static load total would be less than 25 kilonewtons. Each track supports vehicles suspended below it. Fully loaded WAN vehicles are light, under 400 kilograms for intercity vehicles and 300 kilograms for non-intercity ones. These are supported by 8-wheeled bogies that provide the vehicle-track interface. The 2 bogies supporting the vehicle car are about 5 meters apart. Individual vehicles are often formed into trains. On intercity guideways, the trains are more than 15 vehicles long. On arterial guideways, trains are seldom longer than 4 vehicles. On all guideways, the headways between trains are more than 50 meters, so no track ever supports more than 1 train. A train of 4 vehicles on the arterial guideways would then have a dynamic load less than 12 kilonewtons. Even if each track had such a train, in the span of a single tower, the total static and dynamic load on the tower would be less than 75 kilonewtons. That would require diameters for each of 3 stainless steel rods for the column less than 10 millimeters. The rods for the expressway and intercity guideways would need to be more substantial. Guideway spans have cable support points every 4 meters along each track. This ensures that the tension from the static and dynamic load for each cable are about 10 kilonewtons. There would be a small multiplier for the dynamic load. This can be safely dealt with by commodity cable. Each cable runs through a spool in the support column, from a mount point on one side of the guideway to a point the same distance and opposite angle away on the other side of the column. This compensates for the component of the static load that runs perpendicular to the guideway. It is also part of the mechanism for raising the guideway during construction. On standard spans, there are 2 25-meter-long track modules on each side of the column. All spools are attached to a rod that runs up the center of the column. Once all cables are attached to the appropriate module mount points, the rod can be turned to raise the modules. This is assisted by small hydraulic lifts under each module that assist and stabilize the raising. Appropriate gearing and varying spool dimensions would allow for the widely varying lengths and rates of change of the cables based on the distance from the column. This mechanism allows for rapid assembly and maintenance when needed. As noted, the lateral loads from the wind or vehicles are handled by guy wires. Along routes in urban areas, the guy wires would usually be anchored in nearby buildings, well above ground traffic. In rural areas, they would be connected to small piles. The full cost for a guideway network is primarily just a sum over the types of guideway of the unit cost for that type, times the number of units of that type. We use route, guideway, or track kilometers as our units. To understand all costs for the WAN network, we provide a comparison to the costs of the Chinese high-speed rail network. These are drawn from a study commissioned by the World Bank in 2014. On average, the Chinese high-speed rail costs were about 18.3 million US per route kilometer. The yellow items at the bottom are amortized system costs, while the others are guideway specific. We have already covered the WAN vehicle fleet costs. WAN has no stations or any other post-deployment buildings other than a small number of module maintenance garages. The facilities for vehicle and guideway module manufacture can largely be repurposed or disassembled after initial deployment is completed. WAN deployments have little or no justification for interest fees or contingencies. In the US, the entire network build could be paid for by diverting the government cuts expenditures for the 2 years during which a full deployment could be completed. Most deployment risks should be able to be accounted for in the planning stage. WAN planning costs would be minimal. Most routes simply run along existing cuts guideway rights-of-way. WAN guideways have no need for a high-speed rail-style electrification of delivering high amounts of electricity to rapidly moving vehicles. WAN vehicles are battery-powered. Their energy consumption rate is always low. They have a reasonable range with the small propulsion module batteries. Those are recharged, even while moving, by dynamically coupled energy modules. The energy system discussion provides more details. WAN has no need for signaling. All vehicles are in constant communication with nearby vehicles and Wi-Fi routers in the guideway support towers. The tracks for the Chinese high-speed rail systems are standard steel rails on large concrete steel-reinforced beams manufactured in small, movable factories within 8 kilometers of a deployment site. These beams are moved into position by even larger specialized vehicles. As we have described, the WAN tracks are much lighter and cheaper. Using retail prices for the chosen beams, track materials, cables, and covers, the cost per track kilometer is about $70,000 US. Deployment component cost should be substantially less. The $470,000 indicated here is the weighted average based on US extents of the track cost per route kilometer. The civil works dominate the capital cost of all cuts, road, and rail guideways. For the high-speed rail routes, there are 3 types of such works. Embankments are raised earthworks with adjacent fences or ditches. These do not allow ground traffic to cross. High-speed rail, viaducts, and bridges have massive structures to support the massive tracks and trains that pass on them. Where the tracks need to be well above ground, as with most bridges, the support structures needed become prohibitively large and expensive. Tunnels are used where going around a vertical obstacle or flattening of viaducts would be too expensive. However, tunnels are also expensive. They also introduce air pressure and noise issues at tunnel entry. The numbers in each category reflect the per kilometer cost. The civil works cost per route kilometer is the weighted average of the cost and length of each of the 3 types. WAN has no embankment equivalent. That is why WAN guideways do not block ground traffic. WAN routes would avoid most tunneling, except where desired to maintain top speeds through the largest urban areas. With that exception, WAN guideways are the very low-cost viaducts specified earlier. The WAN civil works are minimal. Poles need to be created for the piles that support the towers and provide guy wire anchor points. The piles are then inserted and the tower columns or guy wires are attached. The cost for the arterial guideway support columns and their piles would be less than $200,000 per kilometer. Expressway and intercity columns are more expensive. Collector columns would be slightly cheaper. Labor for these civil works, along with transporting, raising, and final assembly of track modules, would add about $20,000 to the cost per guideway kilometer. These tasks could be carried out by small crews, using the raising mechanism described earlier, at a rate of 1 guideway kilometer per week. The $310,000 indicated here reflects the fact that there are 2 guideways on either side of the road for the IS arterial and expressway WAN routes. As with the Chinese track assemblies, the construction of the modules would be done in small factories that are continuously assembled and disassembled to be near deployment sites. The factories would assemble shorter beam and track lengths with the covers and cable connectors. All of these would be manufactured elsewhere. The assembly should be almost fully automated. For high-speed rail systems, land acquisition costs can be one of the most variable costs. They sometimes even prevent deployment in some locations. The vast majority of WAN guideways use cuts, road, or rail rights-of-way. For these, the acquisition cost is 0. Further, for these, the WAN civil works are trivial. There are only a few exceptions to WAN not using cuts, guideway rights-of-way. Short segments used for spanning rivers where a cuts bridge would have been too expensive or too intrusive. The locations where these could be built and still have useful shortening would in most cases be flexible enough to bypass any significant acquisition costs or issues. Due to the light mass of the guideways and trains, even wider rivers may be spanned cheaply, using other paths like the power line corridor indicated in the LAN example to decrease the size of LAN neighborhoods, putting WAN loops closer to more locations. The need for straightening and or flattening the guideway on some high-speed intercity segments. As with the river spans, all areas under the guideway are unaffected by its presence. The only issue is the small ground footprint of the towers and guy wire support points. This could largely eliminate acquisition costs and objections to that deployment. Freely available software and data would allow any person to explore the possible paths. This chart shows the cost for a WAN network for the US based on the 2021 extents of the CUTS road network. The road types determine the WAN guideway types. The costs are broken down into the various WAN guideway types, using the extents of the corresponding CUTS roads, separated into urban and rural domains. We have assumed that small fractions of CUTS collector roads have WAN guideways. This would result in larger LAN neighborhoods, particularly in rural areas. However, a higher rate of faster LAN vehicles would provide a more cost-effective and only slightly slower trip model in such areas. The entire WAN network for the US would be about 1.1 million guideway kilometers, with about 870,000 route kilometers. This could be built within 2 years by a labor force of less than 100,000 workers. The indicated capital cost of about $670 billion is about $2,000 per capita. As noted earlier, volume purchase prices that would be made for the actual deployments, or some better design choices, would likely reduce this. Note that this is a one-time capital cost that is about what US governments spend today on CUTS over 2 years. There would be subsequent costs for network expansion. This could include building a small backbone network, adding more routes along collectors, or expanding into greenfield areas. However, those costs would be insignificant relative to the initial build cost and can be spread over multiple years. The only significant remaining cost is the energy infrastructure, which we discuss next.